All right, before we dive off into the numerical problem on design, let's set up quick context here. All right, so let's go back. Remember, basic flexural stress equation, sigma equals my over I, probably one of the most famous expressions and models we have in all of our study here. Right, and we take that, and of course, we're typically interested in the maximum. Right, sigma max equals mc over I, where remember, c is that distance from the neutral axis or the centroidal axis out to the outer fiber, either to the top or bottom, right? Whichever is the longer of the two distances, right? So sigma max equals mc over I. The c and the I are just geometric properties. And so we will take that I divided by c, right? Really the other way around, right? And we'll turn that into just capital S. That's just the definition of capital S. S, the elastic section modulus. Just simplifies the expression, puts all the geometric properties into one, right? So sigma max equals the applied moment divided by the elastic section modulus, right? Now, that's just one part of the equation, right? That's the demand side. What's the maximum stress that's induced from the maximum moment in the beam cross section, right? Now you go down to the strength side of things, and we got the signal allowable is equal to some critical or criterion stress divided by the factor of safety. For bending, that's oftentimes about 1.5, right? And so we'll be looking at a lot of steel cross sections and some timber cross sections, and oftentimes in those building codes, we use a symbol for the yield stress as capital F sub y, right? And oftentimes then the criterion stress is the yield stress. So F sub y divided by the factor of safety. You see right up here, this is one of the numerical examples we'll be doing very soon here in another video. Example B3.1. It's a steel related one, and a steel that's A992, grade 50. And it turns out that that grade 50 refers to the yield stress, which is 50 KSI. The ultimate stress or strength is 65 KSI, but we'll be designing based upon first yield. Right, so sigma allowable is equal to Fy over Fs, and our sigma max equal to M over S. We want the allowable stress, the strength, to be greater than the demand, right? And so when we partner all of this together, then we can set sigma allowable equal to sigma max. We've got an applied or demand level of the moment, and we can then determine what the required geometric property is of the cross section. That'd be your capital S. So the S required becomes the moment demand divided by the allowable stress. We do have to keep track of the units, right? Remember, the moment is in terms of foot times length, and then of course stress is the force times length, and the stress would be of course force over length squared. So you have force length over force over length squared. The force cancels out, the length squared comes back up here. We have length cubed, which is consistent with S being defined as I over C. That's length to the fourth, that's length, so we get that reduced down to length cubed. Right, now, the other part of what we're going to be doing here in design is oftentimes looking at steel cross sections. And so many of the steel cross sections that we're going to be using are these I-shaped members, those wide flange cross sections. Remember that that's what this is. The two outer edges are called the flanges, and the outer surface of the flange and the inner surface of the flange are both parallel to each other. That's what makes it a wide flange shape, as opposed to this other shape I've got here, which is, although not made of steel, it is made of, in this case, of wood chips and epoxy. But remember, this one's an S shape, where the outer edge, outer surface here is not parallel to this inner surface of the flange. Right, so we'll be, a lot of them that we work with are these steel beams. Now, the steel manufacturers understand what these structural mechanics are all about, and the folks like us, the engineers, are looking for all kinds of shapes that are off the shelf that will do exactly what we want with the least amount of material, and presumably that would mean least cost. It's not, because availability and how often we use something then is related to how often they produce it, and therefore there's a cost difference that's not just purely about the least amount of material, right? So sustainability is not always about material side, it's also about the other dimensions that are involved here. Okay, so the the reason why these things, these eye-shaped cross-sections look like they do and they're produced this way is because you've got one second moment of area that is larger than the other. We're trying to take that material that we have, that specific amount of steel, push it out to the edges as far as we can go without creating too skinny of a web, and that will give us this IXX larger than the IYY. Right? That's a good thing for us. It does create some other potential issues that you will study if you ever take the steel class. So for instance, here's a beam. Its cross-section looks a little bit like a I shape, right? This is actually a little bit more like a reinforced concrete shape as compared to that steel one that I just showed you, right? If I turn it so it's weak axis bending, right? If we do it that way, it's actually very flexible. If I do it this way, it is a lot more stiff. And that's because of the difference in those eyes, right? But it also turns out, and I'll do it this way now, I'll bend it in the plane and you can see how it actually will then warp. That's called lateral torsional buckling. And so what happens here is that in that tall, skinny cross-section, it doesn't have a lot of resistance to bending out of plane. And so we get something here in the sense of having IX being greater than IY. That's a good thing, but it'll turn out that later on when you get into real design, you'll have to worry about how do you brace that compression flange so that you don't have that rolling out of plane, that lateral torsional buckling phenomenon. In this course, we're going to ignore that lateral torsional buckling, and we will assume that we're working, especially with the steel shapes, that we're working with this kind of situation. If it's not stated in the problem, then that's what you're going to be working with. Now, when it comes to selecting the actual shape that you want to use, you're going to go to the appropriate source, and the steel construction manual is one of those appropriate sources. We got all of these tabs in here, and the very first tab is for these wide flange shapes and the other typical steel shapes. It's got all kinds of geometric properties in there. You have a subset of that, right? That thing costs about $250 or so right now if you are not a student. If you are, then it's about half of that, right? But in your textbook, right, you've got some of these tables available to you. For instance, we've got back here in Appendix D, you have the material properties, and you'll have them in both the SI units and in US units. So you have to be aware of what you're doing there. Usually the numbers are so different, it's pretty apparent which one you're using. But Appendix D will give you a lot of material information, and then you will also have then in Appendix E a subset, a very small subset of these geometric properties of the W shapes. Okay, so we're about ready to charge off into one of these numerical problems, but this is going to be the key expression right here that all comes from what we've been studying in the first two lessons in this beam plot.